Hi, this is Mr. Manley. I'm going to do just a little review here of systems of equations. I've got a couple of equations here, and when we have more than one equation, that's called a system. This is a system of two equations with two variables. When we have a system like this, we like to be able to solve for x and y, right? And I just want to review and look at some of the ways that we can do that with this system. So first of all, we have substitution, right? So if I take the first equation, say, and I solve it for y. See if this makes sense to you. I could say that y is equal to 1.4x minus 17. You see what I did there? I moved the y, isolated the y on one side, so I had a positive y, and then I subtracted 17 from the other side, and then I just reflected them, so the y's on the left. Just because that's the convention that we like to see, right? We always typically put the variable that we solve for on the left. And then I've got y, and I can substitute this, since I know what y is, I can substitute this in this equation for y. So let's do that. And I'll have 0.8 x plus 6 times 1.4x minus 17 equals negative 10. I'm in trouble moving the screen around. I want me to do with 2 fingers. Okay. All right. So from there we can solve for x, right? Now I'm going to have the 0.8x and then 6 times 1.4, right? And that is going to be 8.4. So I'm going to have this 0.8x, and then I'm going to distribute the 6 and have 8.4x. So 8.4 plus 0.8, and that's going to get me to 9.2. So that's 9.2x. And then I had this 6 has to distribute to this minus 17 as well. So that's going to get me minus 102 equal to negative 10. So isolating x, get 9.2 is equal to 92. If I add 102 to both sides, then divide by the 9.2, divide by the 9.2, and I'm going to have x is equal to 92 divided by 9.2, which is 10. And then on any of these systems problems, once I solve for one variable, I want to back substitute and solve for the other. So I would take the 10 here, and I go, therefore, y is equal to 1.4 and then x is 10, minus 17. So that's 1.4 times 10. 1.4 times 10 is 14, minus 17 is negative 3. And that would be my solution. Anytime we're working with a system, typically, or a good way to represent your solution is with a point. The idea being that that's where these two equations intersect. They intersect, these two equations intersect at this point. Which leads us to another way of solving this. Let's look at it graphically, okay? So if I take, let's erase this. And we're going to get ourselves a graph, okay? Let's go there. Let me make this a little bigger. And there. Okay, so I've got 1.4. I think before I do any sort of scale here that I'm going to want to know what I'm dealing with a little bit. What would make you happy? I mean, I think what makes students most comfortable with equations like these would be to write it in slope-intercept form. I don't know if that's the best idea here, but let's take a look at it. So I would have y equals 1.4 x minus 17. We've seen that before, right? And then this other one would be y equals, all right, so I'll be doing a couple of steps here. With this, it'll be the 0.8x will be over here, then that'll be as a negative, right? And then we'll have the minus 10, and then we're going to be dividing by 6. You see that? So I don't know how convenient this is, but let's go ahead and continue with it. So what do I have? 0.8 divided by 6 is going to be 8 over 60, 4 over 30, 2 over 15. Just working with some fractions there that are equivalent to 0.8 over 6 when I multiply it by 10 over 10 and then simplify it. So 2 over 15, that's going to be the slope. It'll be negative 2 over 15 x, and then minus, what would this be, 5/3. Okay. Well, this, I don't think this graph is really helping me too much here. Let me get this out of the way. I'm going to make this a little smaller. And now let's go ahead and put a graph here. All right, so we'll get a x and y axis, and then we're going to have to pick a scale, huh? Okay. I mean, I think I could go 1, 2, 3, 4, 5. 5. 1, 2, 3, 4, 5. I kind of lost my space there, though. So I'm going to go 1, 2, 3, 4. 1, 2, 3, 4, 5. So I'm going to put 5 right here. And then 1, 2, 3, 4, 5. So that'll be 10. And that'll be 15. Okay. And then on the other axis, I'm going to go, I guess I'll probably just do the same. 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So right there. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, well, let's see if I can graph these with this scale here. So the first one is negative 17. So I already don't like that, because that's going to be down off of my screen. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There. 1, 2, 3, 4, 5. There. Okay. So it's going to be down off the screen here. Right there. That's where negative 17 is, all the way down there. And then I'm going to have a slope of 1.4x. Well, I want to know what that 1.4 is as a rise over run, right? So it's 1 4/10, which is 14 over 10, which is 7 over 5. Get that? 1.4, 1 4/10, 10, 11, 12, 13, 14 over 10, simplified to 7 over 5. So I've got a slope of 7 over 5. That should be pretty manageable. Let's go down here and see if we can do 7 over 5. So I'm going to go up 7 and over 5. And that's going to put me right there. And that's all I need for a graph. I just need 2 points, and I've got 2 points. I've got that point, and I've got that point. Incidentally, we're not going to have, you're not going to do it this way typically, but I want you to understand the graphic way. All right, so I'm going to connect those 2 points. Doing a ruler here, but all right, there we go. All right, so there's the 2 lines connected. Are the 2 points connected to make the line. All right, let's look at the other one. The other one's negative 5/3. Negative, that's the y-intercept, right? So the y-intercept is negative, this is negative 5/3, which is negative 2/3, right? Negative 1 2/3. So let's graph that. It's not a very friendly point, right? 1, 2, 3, 4, 5. So that's 1 2/3. So it's like it's in here somewhere. Negative 1 2/3. Not very exact, is it? And then I need to do negative 2. So that's down 2. And then a run of 15 can be way over here. All right, so I went down 2 and over 15 because of this negative 2 over 15. All right, let's connect those 2 points there. Let's see, get my ruler on here. All right, connect those. All right, so the point of intersection you can see is right there. All right, well, where is that on my graph here? That's at, looks like it's at about 10 for x and a negative 3 for y. Remember that? That's what we had when we solved it, 10, negative 3. So there it is graphically. Probably not something that I would ever do to solve this, but really important, I think, to understand. That's what this means, or that is a way of conceptualizing what's going on with this system. It's 2 lines that are intersecting, and when I solve this system and I get this solution here, 10, negative 3, this is kind of or this is at least one way of saying what it means. It's where those two lines intersect. All right, so that was the second way. We looked at substitution. We looked at it graphically. Now I'm just going to keep looking at the same system, just to review the ways that we can solve this. So the other one that I want to look at is the linear combination, is what it's called. You might not know it by this name. You might not use that name. But you might know it as subtraction. Maybe you say, oh, we'll subtract the equations. So what I'm going to do is I'm going to multiply this first equation by 6. Okay? So I'm going to get 6 times 1.4, and that's going to be 8.4 x. And then when I multiply this by 6, the y, I just get minus 6y. And that was what I was really focusing on here, minus 6y. And then equals 6 times 17 is 102, right? And then in the second equation, I've got 0.8 x plus 6y. So that's why I multiplied this first equation by 6, was so that I'd get a match of 6 and negative 6. Okay, and then negative 10. Now I can just add them, because when I add these here, these are going to zero out. So what happens when I add those, I get 9.2x, 0y, and 92. Well, you should remember that, or you might remember that from the first problem. We got to this point before. 92 divided by 9.2, and that gave us our x is 10, which we've seen twice now, that's the solution to this system. X is 10. And then if I plug that in, of course, I'm going to get negative 3. So those are 3 ways of approaching a system of equations. Just a reminder, at this stage in a pre-calculus class, that you've probably seen this as well. I could do this as x is equal to dx over d, and then I'd do this determinant. Solving for x, I'd put a 17 and a negative 10, and then I'd use the y coefficients, and then this denominator is just going to be the coefficient matrix, 1.4, negative 1, 0.8, and 6. And then I'd do those 2 determinants. So the top one would be, I would go this way, 17 times 6, and I would get 102, and then I go minus, and then I go this way, negative 1 times negative 10 is 10, and then on this bottom one, I would go this way, 1.4 times 6, and that would be 8.4, and then minus, I go this way, and that's negative 0.8, so that'll be minus, I'll just write it like that, minus a negative 0.8, and what do I get? I get that 92 over 9.2 again, and there it is again, 92 over 9.2, and that's equal to 10. x is 10. So these are all ways of approaching a system of equations. There are other ways as well. But as we get into this topic that I'm kind of focusing on here, that I am focusing on, this system of equations, what we're really interested in are substitution and linear combination. Graphically is to keep sense of things and make sense of what we're doing. Okay? So that's it by way of introduction. And in subsequent videos, we probably want to be looking at higher, larger systems where we have 3 variables.